So we're going to talk about the last property of waves with respect to light. That's going to be polarization. So I have a light source here shining up onto my ceiling there, right? And I have these three filters here. And so what we're going to look at is what happens to the light once they go through these filters. So there you go. Put the light source or this on top of there. Start to look directly into the light source, but there you go. So once again, without the filter, with the filter, without the filter, with the filter. So you can see once light has passed through this filter, which is going to be called a polarizing filter, the intensity of the light is diminished, right? So we'll talk about why. If you remember what polarization is, you should start to be able to think about what's going on, but we'll come back to it. All right, now I'm going to take a second polarizing filter. So here we go. So I'm going to take a second polarizing filter and I'm going to put it on top of the first. Okay. All right, well, we see another diminishment in the intensity, just a little bit though, not as much as the original one, right? So there we go. So diminishment in the intensity, first one, second one, first one, second one, right? Not a huge change there, right? First one, second one, not a huge change. First one, second one, wait a sec, what? Where? What? Hold on a second. First one, second one. That's a huge change. What? Oh, that's sort of weird. What happened there? First one, second one. Hold on. First one, second one. First one, second one. What's going on there? Well, I'm cheating. This is so much more fun in the classroom. But here you go. Watch what happens here. The second one on top of the first one, right? But what I did is I switched it when it was off film and I turned it 90 degrees. The intensity went just about down to zero, right? Turn it 90 degrees again and the intensity went back to what it was with just one filter. So one filter, two filters, one filter, two filters, and the light almost goes away. So what's happening there? And what's happening there is what's going on with the polarizing filter. So we're going to go to the notes now and try to explain that. If we were in class, I would have tortured you with sleight of hand for a solid 15 minutes before we figured it out. But oh well, such is it not meant to be. Here we go. Turn actually the lights in the kitchen back on. And we're talking about the polarization of light. So what is polarization again? Well, remember that polarization could only be done to a transverse wave. So let's talk about a transverse wave. We said with a transverse wave that the vibrations of whatever's vibrating is perpendicular to the direction of energy transfer, right? So in other words, if the energy was traveling to the right, I could be vibrating up and down. I could be vibrating in and out of the page. If the light was traveling up right at the camera, I could be vibrating up down like this. I could be vibrating left right. I could be vibrating on this diagonal, this diagonal. Remember we said that there was an infinite number of planes of polarization or vibration for a transverse wave. And that's what's going on here. So if I look here, let's just pretend, sake of argument, let's say this is a beam of light shooting out at your face. In a normal beam of light, which we would call unpolarized light, because most light sources don't produce polarized light. They produce unpolarized light. There's something vibrating. So like once again, the direction of energy transfer is right up at the camera. Some portion of the light is vibrating up down. Some of it is vibrating left right. Some of it is vibrating on this diagonal. Some of it's vibrating on this diagonal. I'm not going to draw every diagonal. Some of it's vibrating on this diagonal, right? An infinite number of diagonals. That's what polarized light looks like. What happens is when you go through a polarizing filter or a polarizer, remember what polarization is. It's a process by which only one one plane of polarization is transmitted through. So every polarizing filter has what's called an axis of transmission. It's not really slits. There's something else going on there, and I'll talk about it in a second. But let's say that this has an axis of transmission of up-down, like this. That means when the light goes through, let's see if this polarizing filter is placed over the light source, what we would have afterwards is only the up-down light would get through. Now, it's not just the up-down light. If you notice, if it's just the up-down light, the intensity of the light after going through the polarizer would be almost nothing, right? It just got dimmer, but not like entirely dimmer. The reason is, if this is, we'll call this intensity original, what happens is after you go through a perfect polarizing filter, it cuts out half the intensity. Well, half, but only one orientation got through and there was an infinite number of them. But really, let's say this diagonal has up-down components. So this axis of transmission lets through all components parallel to the axis. Okay, so this one lets through any component that's up, down, and blocks out all components that are left, right. That's what that polarizing filter is doing. So why does it do that? How does it do that? Well, I'll let you know. In this polarizing filter, there are a series of polymers. If you remember what a polymer is from chemistry, they're long chain molecules. And what happens is the part of the wave that is along the chain actually resonates with the chain and gets absorbed, and the stuff that's perpendicular to the chains gets through. So it's not acting like slits so much as it's a resonance phenomena, and that's what the polarizing filters through. So they let through anything that doesn't resonate with the chain molecules and absorbs everything that resonates with the chain molecules. So, polarizing filter. And so that's what happens when you go through one polarizing filter. But what happens when you go through a second polarizing filter? Well, this is where things get interesting. So let's say the second polarizing filter has an axis of transmission that was the same as the original polarizing filter. Well, after this, all the up-down light is only thing that's left. Afterwards, there should be no change in the light going through that second polarizing filter because this has already absorbed all of the left-right light. Now, you did notice in my demo that there was a slight diminishment when going through the second polarizing filter. The reason is this: in a perfect polarizer, all of the left-right should have been absorbed, and it wasn't. This probably was closer to about 60%, and then this got it closer to half, but you'd probably have to go through a bunch of polarizing filters whose axes of transmission were parallel before you actually got to half in the real world, okay? But what happens if the second polarizing filter, so now we put the light through a second polarizing filter, whose axis of transmission is perpendicular to the first, right? Oh, well, now you go through the first and only up-down light exists. You try and go to this that is going to absorb anything except for left-right light, and what should happen is, at the end, we have no light, right? That the intensity has become zero. We blocked out all the light, because first we blocked out all the up-down, then we blocked out all the left-right. There's actually a fairly complicated relationship between, if we define an angle between two consecutive of polarizing filters, right, as being something, let's say, I think it's called phi in that equation, that when phi is 0, right, you get half of it. When phi is 90, you get none of it gets through. And if you're thinking 0, 90, 0 is like maximum, 90 is 0. It sounds like a cosine. You're right. We're never going to use this equation just for interest here. I'll tell you that The intensity that you get at the end of the second polarizing filter is the intensity of the previous polarizing filter times cosine squared of that angle between the two axes of transmission. It's something called Malice's law, but we're not going to really talk about it. Just I thought I'd put it in there for interest. So there you go, polarization of light. Now, uses for polarization of light, obviously, polarized sunglasses. So what do polarized sunglasses do? Oh, well, they cut out, they make the light coming into our eyes less intense, which is good for our eyes because our eyes strain when light is too intense. So that's really good. But what's the main thing for the reason why you wear polarized sunglasses? Well, you do it, and they were first invented to help sailors, specifically with glare off the water, right? So what happens here is if this is water, and you have light coming in to water, when light gets reflected off of water, it becomes polarized. So here's unpolarized white light coming in, and here it is polarized. Very specifically, when light is polarized off of water, what happens is it is left-right. That's what's left, is the left-right or horizontal component of this. So if I'm standing on my boat here, right, I don't want to see glare. I'm very tall, apparently. I don't want to see, and there's my sunglasses, okay? I don't want to see glare. I just want to see light. And so polarized sunglasses very specifically are polarized up, down, so that no glare can get through them. Same thing with ski goggles, folks. If you have a nice pair of ski goggles, when light hits snow, snow is water, it gets polarized left, right, and if you don't want to see the glare off the snow, then you have polarized ski goggles that do that. There's a lot of other applications for polarized light, but these are the two most common things that I wanted to talk about. So a diminishing intensity because part of the light is being cut out. If we have two polarizing filters, how the two polarizing filters are with respect to each other determines what happens. Just to finish this off for fun, it gets kind of complicated because it does have to be two consecutive polarizers, because I'm just going to show you what happens here when I have three. So here I have the first polarizer, second polarizer, up. How must that have meant? Well, nothing really changed. So these had parallel axes of transmission. Now they are perpendicular to each other. And even still, you can tell that these aren't perfect polarizers because that should block out all the light, but it doesn't, right? But let's say I do it at some angle, say like 30 degrees, right? I take a third polarizer and I put that on top, no change, right? But if I have this, I have to go perpendicular to the second in order to block out more light. But if I have something like this, you know, where theoretically, well, actually, let's get this. Those two polarizers are perpendicular to each other. If I put a second polarizer in between, darn it, a second polarizer in between, that's not perpendicular to any of them, it doesn't work. It's got to be two consecutive polarizers that are perpendicular to each other in order to get that blocking out. So if you're ever buying polarized sunglasses and you want to make sure that you're not being ripped off, what you should do is take two pairs of them, put the lenses up next to each other, and move the lenses back and forth. If you don't see a change in intensity by changing the angle between them, at least one of the glasses are not polarized sunglasses. So there you have it, polarization of light. And remember, what does that prove? That proves that light is a transverse wave, because only transverse waves can be polarized.